Let's see here. This is a brief summary. We're going to get into timing files and also how the bullet signal relates to this single subject analysis. Okay. Timing files, you need to make sure that those things work, that they're right. If they're off if they're off by a few seconds, it's going to throw everything else off, and there's nothing you can do about it. There was one lab in the Northeast that I was consulting for, and they'd collected maybe 70, 80 subjects, and they hadn't looked at any of this. They hadn't looked at their timings at all. That's crazy, because this is something you cannot recover if it's not there. So if your stimulus presentation software, ePrime, presentation, whatever, yeah, that's what I did. It's like, yeah, because there's absolutely nothing you can do to recover it. Right? If for some reason didn't output it, we can't do anything. So always need to check it. Always need to make sure that it makes sense. Now with OpenNeuro, we have this this timing file that comes with it, showing what the onset was, what the duration was, and what the trial type or condition was. Okay. The first script that I had you guys run was something like maketimings.py, right? If you look at what's going on, there's a lot of Unix stuff, I'm not going to cover it, but it formats everything first in FSL format and then transforms that into AFNI format. That's for a few reasons, because I first gave one of these workshops in FSL, and then I thought, I already have the timing file. There's a very easy way in AFNI to just convert from FSL to AFNI, so I just use that command on it. So this is what you'd see with something like FSL, right? So this is the original spreadsheet in, say, the VI editor view. We transformed that using a script into this 3-column format with onsets in seconds, duration, and then a parametric modulator. That's FSL format. And then we use another script called timingtool.py to just simply transform this into AFNI format. There are a couple different kinds of timing formats. Either one is acceptable. One's called local times, one is called global times. Local times, 1 row per run. Okay, so this is all within a text file, either called congruent.1d, incongruent.1d. Remember, there are 2 runs. Okay, so let's say this is the incongruent.1d file. There was one instance at 0 seconds, one at 10 seconds, 40 seconds, and so on. This is showing the timing in the first run, right? And then also in the second run. Notice they're all relative to the start of their respective runs. That is local timings. You have another option called global timings. Some people prefer that. I'm indifferent. They do the same thing. But in that case, this would get transformed into 1 long row, or 1 long column. Okay, so 1 onset per row, and you basically concatenate all these things together.
And then the timings from the second run are
yes.
Run plus.
Yes. So instead of this one starting at 0, it would start at whatever the total time for the first run was. Yeah. So there are different options. I wish I could show both of them, but just options. It really is up to you. And the reason I bring this up, I also want to direct your attention to, if you use something like ePrime, do anybody here use ePrime? Okay, I'm sorry, but a lot of people do use ePrime. If you do want to use ePrime, what I find most useful is to write everything out within the ePrime environment. Okay? So within the slides, I included a link to a blog post about how to do this. It looks pretty complicated, but once you break it down, it's not terribly sophisticated. It's up to you. I mean, some people prefer to create their timing files from the output from ePrime or presentation or whatever they use. But this one, creates a timing file that I know is in the format of whatever I'm using. So it can save you some time. Just to give you some options if you want. Okay, so let's revisit the bold response and then go on to first level model. So remember, we have this thing called the hemodynamic response function, which is this stereotypical pattern that we see in response to a single instance of a condition. Now let's get a little bit more sophisticated. If, let's say, the condition was on for 10 seconds, 20 seconds, the shape of that HRF is going to look a little bit different. Okay, it's going to be a little bit more extended over time, and it's also going to plateau at a certain point. So in red here, this is the actual duration of my stimulus. It's being convolved with this HRF in black, and it's creating this boxcar regressor. So it looks like it's pretty like a pretty high amplitude, but still we're going to be in the modeling part. We're going to be modulating this to try to best fit the data. All I'm showing here is that the HRF tends to be extended even further in time depending on what the nature of the stimulus was. Presented for a long time, it gets extended in time. If it's very short, you tend to see more of the pattern of the HRF. Let's see. Revisiting this just once more. Okay, so remember noisy time series, what we saw in the AFNI viewer. Our mission in single subject analysis in 3D deconvolve is what the command is we're going to use, is to recover what the signal looks like for each condition from this more complicated time series output. Okay, that's the whole idea behind what we're doing. We call this a mass univariate approach because we're fitting a model at each voxel. I got lazy and just copied this from an FSL lecture I gave. But your design matrices are going to look something like this. Okay, this is your first time with neuroimaging. This is going to look a little weird, but let me walk you through it. In fMRI analysis, we represent our model as a matrix. Okay? And in these matrices, time is represented as going from top to bottom instead of traditionally left to right is how we think about it, right? And what you can see is in these lighter bands, that is when there's an onset of a certain condition. So we're seeing the HRF in response to each of these conditions when it occurs, and it goes back to baseline. And then if we superimpose our fitted model on top of the time series, so this blue is this jagged, really messy time series that we get from the raw data, even after we pre-processed everything. Now, what this model looks like superimposed on this is in red. And what we see here is that the bumps for each of these conditions are modulated either up or down based on how it's going to best fit the data at this particular voxel. Right? So remember when I showed you when we convolved all the responses together, there's bump here, bump here, bump here. In that case, they were all the same amplitude, but when the fitting part happens, we're modulating the height of all of them to try to best fit this actual time course rate here. So if we find out that for one of the conditions, we need to scale this amplitude by quite a bit to fit that time series, that suggests that in that voxel, it's more responsive to that condition. Make sense? That's an assumption, right? We're assuming that the signal, which is related to blood flow, is somehow related to neural firing. And so that condition must be eliciting some kind of neural response. And then we create these statistical maps showing what the magnitude of that response is relative to the variance in that response. It's a t-statistic map, right? What's the magnitude divided by variability? That's going to give us some sort of test statistic. I always trip up on that word and it annoys me because I got to say it a lot. I hate teaching statistics classes. Just because of that. All right, so the general linear model. Remember this assumption of linearity. This is why this is very important. If we use one or more regressors, okay, representing those conditions, so in our case we have two regressors. We have congruent, we have incongruent, because that's the only thing that they were exposed to in this particular experiment. We use that to predict an outcome measure, which in this case is that signal that we gather from the scanner. We represent this using matrix notation. So this may be familiar to some of you. Y is the outcome variable. Let's say that time course at a single voxel. So don't think about the whole brain, just think about a single voxel. Within that voxel, we have our regressors specified by, say, x1, x2, x3, if we had 3 regressors. And remember I talked about scaling the amplitude of each of them. That is this beta, also called a beta weight. So how much do I need to scale each of those? And is that amount I need to scale it significant? Those are the main questions we ask during the fMRI analysis. Anything that we can't explain in the time course by any of these explanatory variables goes into this error term. And the bigger this is, the weaker our statistical results are going to be. That's why we try to model every possible thing that we think may be affecting the actual signal. Right? So anything that any button they pushed, anything that they saw or heard during the experiment, we try to model all that to best explain the variability in the signal. Anything left over gets shoveled into a residual term. Okay, so let's walk through this and give you an example with behavioral data, because it really is basically the same thing. If you understand multiple linear regression, which is what this is, that's all we're doing at each voxel in an fMRI analysis. Come on. So let's say that we had some explanatory variables. We're trying to predict something like GPA. We have variables like IQ, drinks per week, and height. Right? So we're going to give relative weights to each of these variables to try to best explain somebody's GPA. Those are our beta weights. And let's say that we found that for IQ, each IQ point, their GPA goes up by 0.05 on average. Number of drinks, it goes down by 0.07. And for height, maybe it's 0.01. But we're also measuring whether each of these is statistically meaningful, right? Is it significant? So in this case, intuitively, it might make sense that IQ, drinks per week, somehow contribute to GPA, but height doesn't, let's just say. So toy example, but we're applying this, we're using it as a surrogate for our fMRI data. Only thing I haven't included here is some kind of intercept. That also is something that needs to be taken into account. And we do model that in the fMRI data as well, as some kind of baseline that gets deflected from. So the long and short of this is our raw time series in gray, and we're trying to scale these HRFs, these individual regressors, by some sort of beta weight to best fit the data. I'm just repeating this a lot because this was something that for some reason I got really tripped up on a lot early on. One of the first times I asked somebody what a beta weight was, he said, "That's really complicated." I was like, damn, that's got to be really complicated if this guy doesn't know about it.
So, this is also something I struggled with a lot when
Yeah.
I started. So you get one beta weight per voxel.
Yes.
That's it.
Yes.
Per
regressor,
sorry.
yes.
Yeah.
Yeah. And in the approach we're going to do, it's averaged across all the trials, right? So you're...
How is
Right.
an average?
Because you're applying that same beta weight to every trial.
Oh, so every
Yeah.
instance in that regressor.
Right. It's not trying to fit an individual beta weight for each trial.
Okay.
You can do that, and we will do that for MVPA analysis.
Right.
You also see it in more complex designs like a beta series correlation, right? That's another instance where you'd want to do that.
I guess it is good to mention that this is what I found actually interesting. That regression terminology is basically the predictor.
Yes.
So it just regresses another terminologies used in fMRIs.
Yeah, we're using the exact same terms. Yeah, I mean, if you understand multiple regression in a behavioral context, it's pretty easy to translate it into an fMRI context. The only thing that's weird is that we have these time series and then people get kind of tripped up about it. But all we're doing is we're trying to match these patterns. We're trying to match this raw signal pattern with our ideal model pattern, right? And we fit it with all these beta weights to try to get the best fit. And once we do that, we can test for whether it's a significant effect or not.
So ultimately, it's the beta weights you do the statistics on.
Yes, the beta weights is what we do the statistics on. And usually, you want to take a contrast between the two, controlling for some sort of dimension or variable, so that you can isolate some kind of process of interest. So with incongruent versus congruent, for example, we're keeping everything the same. We're just changing whether the flanking arrows are congruent or incongruent, right? So all we're changing is the congruency dimension. Okay, and we just do this every voxel. Wait, is this a video? It is a video. Okay. Okay, I have a little script I got to read. So to put this in mathematical terms, each voxel has a time series, which we'll notate as y. And we also have our two regressors, which we'll notate as x1 and x2. Now these regressors constitute our design matrix, which we'll notate with a large X. So far, all these variables are known. We know y, and we also know x1 and x2 from our onset files, which we construct by convolving them, each onset with the HRF. Now, since the next part gets into matrix algebra, I'm going to switch the orientation of the time courses so that it looks more like what you'd see in a design matrix. Normally you think of them as running left to right, but now we're going to depict them going from top to bottom. Okay. So the next part is the beta weights, which is how much we're going to scale each of these regressors to best match y. Right? So this is the amount that we weight each of the regressors, and hence the name beta weights. The last term in this equation is going to be epsilon, which represents the residuals, or the difference between our fitted model and the time course. So anything that we didn't capture in our model gets into this residual term. Okay. Yeah, that's everything I want to say about it.
So when you're doing the statistics on the beta, it's using the residuals that are added into the error term?
Yes.
Okay.
Yeah. So a couple of things at the single subject level, at least, that going to determine significance is the magnitude of the beta weight, what's in the error term, and also the degrees of freedom, which is an effect of the total number of time points adjusted for things like temporal autocorrelation, and you subtract from that the number of regressors in your model. Yep. Okay, any questions about that? Because if you understand that, you're really good to go for doing this.
Going back to that design matrix, at any some time point, it's going to be any of those regressors is going to be having a value of 0 or 1, just like dummy coding the model.
There is dummy coding you can do as part of your model, but not for those particular. You're talking about the beta weights?
Yeah.
No, the beta weight is it's a continuous variable. So you could weight that regressor. It's essentially that beta weight is representing the amplitude of that HRF that we need to scale the trials in that condition by to best match the time series.
Okay.
Dummy coding is something you can do in your model. If, say, you want to divide it by,
Contrast.
say, like male, female, or some other, binary contrast.
Congruent versus incongruent, and stuff like that.
That's not necessarily what I would think of when I'm talking about dummy coding.
Maybe I'm just a little confused. Like, how do you assign the value of any like recursive at one time point?
At any time
If
point.
you go back to that slide, like data matrix.
This one right here? Or
they had there were two graphs.
was it the movie?
Well,
Was it this thing?
I think this one.
Yeah.
So x1, x2.
Yeah.
So those I guess I'm a little bit confused. Like, how do you assign the values of that? Like, so at some time point, like x1 is just like almost like a baseline, but x2 is just like jumping up, right? So what are those values? Maybe
So these also, there are numbers associated with this, but they're also continuous. They're being scaled by a certain amount. We're adding them together at some point. So at each time point, we do have a single number that represents the sum of these two things, but we also have information about what we need to scale them by to get that sum.
So like when, you know how you do that make timing file script and you got the numbers like 10, 20, 30, 40, all those numbers. Basically what that is it took those numbers and wherever like at 10 seconds, it put one of those responses
Yeah.
there.
Yeah.
I see. Okay.
Does that make sense?
Yeah,
Yeah, that's the
I thought, I was getting confused with like dummy coding at this point, this time point,
Right.
like this is like 0, the other one is 1, and like vice versa. Like to
Right,
make sure
yeah.
that we are just canceling out one beta over the other one. But now it does make sense.
Right, yeah. We're not necessarily doing dummy coding in
Okay,
the sense you were saying, yeah. Yeah. Let's see here. Okay. With AFNI compared to something like FSL, first level analysis means we're analyzing the entire individual subject. So across all the runs, all the trials, that's all going to go into a single design matrix. In something like FSL, you analyze each run separately. You analyze the variance in each run separately. And that's just their approach. They try to use it to form a more accurate parameter estimate. I'm using parameter estimate and beta weights somewhat interchangeably. Whether one's superior or not, I don't know. Can't really say. But with AFNI, you can get more into what FSL is trying to do by using something called 3D MIMA, which is a mixed effects model which takes into account variability within the runs. Yeah?
What happens when you have an empty regressor? So,
Good question.
no event,
Mm-hmm.
and the beta value is set to 0?
Yeah, in that case, there's a way to code for it.
So I think in the timing files you just have like a star or a negative.
Yeah,
value.
yeah.
But what happens like statistically?
Statistically, I think that if it's just for that particular run, I believe.
Or I have some subjects who like we have an incorrect response.
Yeah.
Regressor, and there's some subjects who didn't make any incorrect response
Yeah.
throughout the whole
Uh-huh.
all of their runs.
Yeah.
So an entire regressor for them is just for all runs is just -1.
Right. I'm actually not sure how that's modeled exactly. That'd be something I'd ask the people.
Janet actually has this the
Yeah.
entire explanation of that on her website, like
Yeah.
how to runs, contrast, and stuff like that.
Yeah. Sala's referring to Jeanette Mumford, who's
Oh yes.
Yeah,
statistician.
It's just confusing because we were talking.
It's different in FSL than it is in AFNI.
Oh, it is?
Oh, is it?
It's just
Okay.
the way it contrasts against that regressor. So if you were doing correct over incorrect,
Mm-hmm.
she said that that's problematic because FSL treats an empty regressor as a 0. So the
Okay.
beta weight is set to 0, which is what it does in AFNI as well, according to the convert help page. But I was just wondering if you
I don't
had
know.
any other. Okay.
Don't know. That's a good question because it definitely happens, right? If you're trying to model out incorrect or error responses, but I'm not sure. Okay. And second level analysis just refers to a group level analysis across all the subjects. Let's see here. So today's example, we have 2 runs, 2 conditions. And the number of regressors is going to be 2 for the number of conditions plus baseline regressors and also drift and motion. So what this looks like, you'll see this, you actually have already generated this from that first subject. This is the design matrix. Okay, it looks kind of weird. Again, this is your first time seeing something like this. This probably looks like gibberish, right? It looks like a noisy TV screen. I don't even know, do TV screens do this anymore when you have this white noise? We don't even have it anymore. That's too bad. But what's happening here is these first few lines are going to represent your drift regressors. And in AFNI, at least nowadays, they do the drift and the motion for each run separately. Wait, oh, I went back. Okay, these ones right here are the experimental regressors or conditions. Now, AFNI compared to, say, FSL, color codes things a little bit differently. So things that are a little bit darker, think of those as kind of coming out of the screen towards you. That represents the HRF. Right, so if we're going down in time, we come across, let's say this is congruent. That first black notch right there, that actually represents the HRF coming out and then going back in. If we zoomed in, you would see a little bit more gradation where it becomes darker in the middle, but around the edges it's a little bit lighter, representing the ramp up and then the ramping down. So this is what we're trying to fit to each model. And then lastly, we have our motion regressors. It's a typical design matrix. More complicated designs are going to look different, but mostly just within this part right here. It's going to be expanded a little bit. Okay, virtually all studies are going to be modeling drift. So this is like, say nothing's going on. This is where there is a linear increase over time. This is where there's quadratic. Say if there's any kind of trend in the data to go up and then go down that's unrelated to your experimental design, it tries to capture that. That's what's going on with those polynomial or drift regressors.
Is there any situation where you wouldn't add those in?
You should always add in the drift regressors. You always want to be picking up anything like that. For the motion regressors, these days I would always include them. I don't see why not. I mean, studies usually have enough time points and degrees of freedom, or effective degrees of freedom, to model them without taking too much of a hit. I really don't see any reason not to model motion or anything else for that matter.
This might be dumb. Are there 6 drift regressors because they go to the 6th power?
In this case, let me think here. I know that, yeah, these definitely model, say, baseline, linear, quadratic. It's the first time I really looked at this, so I don't know what these 3 things mean, actually.
Okay. I was like, why are
That's a good question, yeah, because it makes sense to include, say, 3 to the 3rd power.
It's the same thing, right, but they're flipped.
They are?
Yeah, so
Here?
if you look at
Second.
the ones from the bottom,
The second.
gone to the top.
Yeah.
The ones at the
Not
bottom
sure.
are the second run.
Yeah, it may be just because I was parceling, this is the first run, this is the second run, and just filled in these with something else. Could be wrong, but that's my reading of it.
Yeah. Okay.
Yeah.
That makes sense.
They changed this recently. It used to, these would all be in the same column, right? These would all be in the same column. They've changed that recently for reasons I'm not entirely sure about. But yeah, it's kind of the same thing over here. I don't think that these represent actual motion regressors for
Right,
run
yeah.
one. They're some kind of placeholder.
Right. That makes sense.
Okay, so let's look at some first level results. Yeah? The first thing I want to draw your attention to, when we did the VI editor, did people feel okay with that? It's okay if you didn't, because it's a weird thing. Were people able to exit from it? I don't think I showed you how to do it. Okay, if you're ever in the VI editor, if you want to get out of it, type shift and then colon, get your colon, and then type Q and then hit enter to get out of it, okay? There are other editors from the command line. There's things like Nano, there's things like Pico. I'm not that familiar with it, yeah.
Before we start, we just like to get, I came a little bit late and also we had to exit out. Some of us had to exit out because we didn't know how to close that.
Oh yeah, sure.
We just take a second to get back. Yeah, we have.
Sure, yeah, let's take a few minutes. You guys want to get any
Yeah.
refreshments, feel free. We will get through everything and you will have some time to practice.